When we talk about charge, things are charged, positive charge, negative charge, okay? Let's go into like chemistry land for a little bit. Some of you have taken chemistry, some of you are taking it right now. Actually, I think all of you have taken chemistry. Or maybe a few of you may be taking it right now. But if we look at a simplified atomic model, you can see there we've got beryllium on the right, hydrogen on the left, and those little grayish dots are those electrons. And the red and the green are the nucleus of the atom, right? And that's where the protons and neutrons are. And so if you can see here, and again, this is just a very simplified model, but sometimes we think of the atom as the electrons sort of orbiting around the nucleus. I know some of you are out there saying, well, Mr. Bob, I've learned recently that's not quite right. And I agree with you. There are inadequacies about this model, but for us today, this works. And so we're going to use it because it works. And again, in science, we make models that work for us to explain situations that we're trying to explain. And this one works for us right now. And so notice each proton, you probably learned somewhere in the past, has a charge of +1. Each electron has a charge of -1. And as long as the number of electrons equals the number of protons, you have a neutral atom, right? In other words, on the right here, if I just do a little math, I have +4 protons. And then I have 4 electrons, so -4, so the net charge is 0. Same thing over here with the hydrogen atom. +1 proton in the middle, -1 electron orbiting it, so 0, total charge is 0, the atom is neutral. But if I take away an electron, you ready for this? Here we go. Here we go. Where's it going to go? When's it going to go? There it goes. If an electron is moved from an atom, then what happens? This charge balance has been interrupted or disrupted. And now I no longer have -4, but it's now -3, which means now I have a +1. I have a positive ion, and the beryllium is positively charged. Okay, a positive net charge because it has more protons in the middle than it has electrons orbiting it. And likewise, if an electron gets added, say, there it comes, do you see it? The electron gets added to the hydrogen atom, let's say, then now I have 2 electrons orbiting the nucleus of the hydrogen atom, and I just have 1 proton still, so that becomes -2, and this becomes a -1, so that would be a negative ion. Okay, so hopefully this is something you've been exposed to before. If not, I'm just doing a brief review for purposes of building upon it. From there, I want to bring us to this idea of what we call the elementary charge, and this is really vital for us in physics. I don't think you talk about this in chemistry so much, but when we say the charge of an electron is -1 or the charge of a proton is +1, or by the way, the charge of a neutron is 0, it's neutral, what we're really saying it has a charge of what we call the elementary charge E. And we say it's elementary because up until recently meaning say the last 50 years, we really thought that that was the most fundamental charge you could have. Like you couldn't have a base unit of charge below what an electron is or what a proton is, okay? And so that got a symbol, the elementary charge E, but in science, in physics certainly, we need to use that and incorporate that into the SI system. So to use that in calculations and equations, we have different units. So the SI unit of charge is what we call the Coulomb. And if you remember, this was one of the, actually no it isn't, because the amperes, yeah. Anyway, this is an SI unit, it's called the Coulomb. I was about to say this was one of the 7 fundamental units, but it actually is not, because the ampere is what's defined. But anyway, I digress. So for this slide, for the purpose of this today, what you need to realize is the following. That when we say an electron has a -1 charge or a proton has a +1 charge, that means its elementary charge is 1e, and there's a conversion that's really important, and I would give it to you on the data booklet, but you need to make sure that you can use it, and you're going to get some practice using it. 1 electron basically has a charge of magnitude 1.60 times 10 to the 19th coulombs. Similarly, the magnitude of the charge on a proton is the same, 1.60 times 10 to the 19th coulombs. The only difference is one is positive and the other is negative, and we're going to see how that plays out here. But this is a really important idea, and an idea that we're going to carry forward. Okay, so a simple experiment we can use to demonstrate the creation of charge imbalances, okay? And you've done this before as a kid at some point. You rub a balloon against your hair, against your clothing, whatever. And when you do that, the wool gains positive charge, and the balloon gains an excess of negative charge. In other words, some electrons are transferred from the wool to the balloon, okay? And so then if we take two balloons that we've done that with and we try and bring them together, we find that they push each other away, okay? The green and orange balloons repel each other. You can see there I've just drawn a very simple free body diagram of the green and the orange balloon when they get in close proximity with each other. And by the way, we're ignoring gravity in these situations. Also, if we try and bring the wool samples close together, you're going to find they repel each other as well. So that's interesting, right? So we can say that like charges repel. In other words, if a positive charge comes closer to a positive charge, each is going to feel a force, a repulsive force, pushing away from the other. And the same thing goes if you get two negatively charged objects. Now notice in the balloons and the wool samples, they still have some of the other charge left, but the only thing we're representing here is the excess charge they have. They have more electrons or fewer electrons in the case of the wool, right? So we're just representing the excess charge. The other thing we'll find out is basically if you try and bring the wool back closer to the balloon, they actually will attract each other, okay? And so we can say that unlike charges or opposite charges attract each other. And this is really important because this brings us to something called the charge model. This is one of those fundamental ideas in physics, really important. And it basically says this, that if we have two negative charges, it's kind of a summary of the last two slides. Two types of charges exist, positive and negative. Like charges repel, and unlike charges attract. Excuse me for a second, I gotta let my dog in. Come on. Okay. So this is a really important fundamental idea, one that you've intuitively understood before, but we're going to use it in much greater detail here. All right, you ready for a joke? Who's ready for a joke? Of course everyone is. Who wouldn't be? Let's do it. All right, the joke. The joke is the following. Hold on, I gotta get something. There it is. Okay. All right. The joke is, why did the bicycle fall over? Why did the bicycle fall over? Why would a bicycle fall over? Because it was too tired. All right. All right. I think someone else contributed to the laugh track too. I like that. Very good. You know what we should do? Let's do this. Yeah, we'll do it next time. Next time we have a joke, I'm not going to do a laugh track, but I'm going to want you all to unmute your mics simultaneously and just laugh, and we'll see what happens. Yeah, that's a great idea. Thank you. All right. Okay, so now I want to talk about something called the conservation of charge. So the conservation of charge says this. It's quite simple. It's like other conservation laws you've probably come across. The law of conservation of charge says that charge can neither be created nor destroyed. But charge, meaning electrons, protons, positive, negative charges, can be transferred from one object to another. But if you take into account all the objects in a system, the total charge of the system has to remain the same. Okay? This is an important idea as well. So we've got charge model, we've got conservation of charge. All right, let's apply it. Let's apply it to a quick sample problem. So here we go. There you see, there's my dog, Dobby. And let's say a dog's fur, like your hair, acts like wool when you rub a balloon on it. A balloon has picked up negative 150 microcoulombs of charge from Dobby. Okay, so I rubbed a balloon against Dobby, and some electrons were transferred onto the balloon from Dobby's fur. So then the question is, how many electrons have been transferred? And then do I have another question? Is B, what is the charge on Dobby? Express your answer in coulombs. All right, let's do this. So letter A says, what do we need to do for letter A? Well, this is a factor label problem, by the way. So if you've been missing factor label, this is your chance. Okay. Now, when I say how many, notice what I'm going to do here is I'm going to ignore the negative sign. We know if it's negative, then the electrons were transferred from the wool to Dobby, or from the fur, excuse me, from the fur to the balloon. Dobby's fur. And it's just a question of how many. So if I have 150 microcoulombs, okay, and I have to get to electrons, I'm going to have to do two conversions here. I'm going to have to go from microcoulombs to coulombs, and I'm going to have to go from coulombs to electrons. Okay, so notice I've set up two conversions there. Now, if you take out your handy dandy metric conversion, we know that what? It takes 1,000,000, or 1 times 10 to the 6 microcoulombs is 1 coulomb. And then we know from the previous slides that 1.6 times 10 to the negative 19th coulombs is 1 electron. So, oops, let me make that clear, 1.6. Okay, so go ahead and do that on your calculator. I'm going to do it on mine. 150 divided by 1, second function e, 10 to the 6. Divide that again by 1.6, second function e, negative 19. And I get something that is roughly 9. If I'm going to stick with sig figs, I'm going to call it 9.4 times 10 to the 14th electrons. Okay, so that's how many electrons have been transferred, 9.4 times 10 to the 14th. All right, and then part B, what is the charge on Dobby? Well, this is really simply an expression of the law of conservation of charge. So if the balloon has negative 150 microcoulombs of charge, Dobby has to have, similarly, positive 150 microcoulombs. But I expressed the answer in coulombs, so that would be 150 times 10 to the negative 6 coulombs, or if I want to be scientific notation, it would be 1.50 times 10 to the negative 4 coulombs. That would be the way I could write it. Okay, let me pause there and see if anyone has any questions about what I just did. Okay, so you're gonna have problems like this in the homework that you have. Let's go a little further. I'm gonna keep going. If you do have questions, you can still write them in there and I'll come back to them. Let's talk about Coulombs Law. Coulombs Law, really fundamental law here in science, in physics. So French scientist Coulomb, he studied this charge and charges and studied sort of the forces they exert on each other. And he discovered the following, that if I take 2-point charges, Q1 and Q2, and let's say, I'm gonna say Q1 is here, I'm gonna say Q2 is here, and they're separated by a distance. Let me pick a different color to make it a little more nicer. And let's say the distance between their centers is R, okay? So there we go, we got Q1, we got Q2, 2-point charges separated by distance R. Then the force that each exerts on the other can be calculated using this formula. And here it is. Basically, you take the magnitude of the first charge, magnitude of the second charge, divide it by the distance between their centers squared, and you multiply it by Coulomb's constant, which is that K value. And poof, you have the force between two objects. So let's make sure we understand what each of these are. While we're doing that, oh yeah. While we're doing that, I want you to think about something. Does this remind you of another law we've studied earlier this year? Hopefully it does. So this is charge in coulombs. And it says distance between their centers in meters. Okay, so that's Coulomb's law. And maybe you made the connection, some of you hopefully made the connection, that this looks an awful lot like, yes, Cade, coming through, the law of gravitation, Newton's law of universal gravitation, right? Because if you recall, let's go back, sorry. You recall that law was G m1 m2 over r squared. So notice we replace the masses with charges. Distance is the same, it's an inverse square law. We just have a different constant. Instead of the gravitational constant, we have Coulomb's constant. So scientists for centuries have been amazed and puzzled by this. And this really suggests that, and scientists and physicists for centuries have been trying to kind of unify this, because if these things are similar and the equations are similar, there's got to be some sort of underlying fundamental idea that maybe is beneath all of this, right? But so far we haven't been successful. Haven't been successful in kind of identifying how this works. And there's something called the Standard Model, which has helped unify like electricity with magnetism, but gravity is still kind of hanging out there and still not fully understood, and how it works with, how it kind of fits into the picture of everything else. That could be a fascinating topic to explore sometime in the future if you wanted to on your own. Okay, so now let's get to the demonstrations. Hopefully you all saw the 5-minute video. If you did not, that I put together with those 3 demonstrations, the tin can, the meter stick on the mouse, and the paper dots. Please go ahead and make sure you see those at some point. And the question I want to walk through with you here is, how can you use our charge model in Coulombs Law to explain the observation of the demo where the glass rod moved the wooden meter stick without touching it? Okay. Typically, I find that students can predict what's going to happen with metal objects, but they get very surprised. And like I said in the video, I was very surprised when I first saw this wooden meter stick demonstration. And so I want to talk through how this happens. Okay, so let's think about something here. Let's think about, we have this meter stick, right? Here's the meter stick, okay? And the meter stick is what we say neutrally charged at the start, right? So at the start, the meter stick has, and I'm going to basically exaggerate things here, but you know, it's got plus, minus, plus, minus, plus, minus, evenly distributed, right, on both ends. You can think of the meter stick as starting out this way, okay? And then I take that rod, and what did I do with the plexiglass rod? The first thing, pretty much before every demonstration, is I rubbed it. I rubbed it with that cloth, right? And rubbing it with the cloth, what happens is it gives excess electrons. And I'm just going to show the excess charge here. Okay, so there's the rod with the excess charge. So what happens? Now, oftentimes students think, and again, this is something that I thought too originally, when you bring it close to something that doesn't conduct electricity, nothing's going to happen. Like, so you bring the rod close to a tin can. Hey, that makes sense. It's metal. Metal conducts electricity. The tin can's going to move. But why would it move a meter stick? Well, let's think through this. You are right in saying that the meter stick cannot. The electrons in the meter stick maybe are not as free to move about as, say, the electrons in the tin can. But if I bring this close enough, this rod close enough, okay, and now I'm going to exaggerate this effect here to give you a sense for what's going on here. What is going to happen inside the meter stick is basically, if I'm a positive charge, remember, like charges attract, right? So the positive charges are going to slightly move, and again, I'm exaggerating the effect here for purposes of this illustration, but you can imagine that in that meter stick, the positive charges are going to move slightly more towards it, but more importantly, and actually physically what's happening, is those electrons that are revolving the nucleus of the atoms, those electrons are going to just move a little further away from all that negative charge that's on the rod. So notice, on average, what I've drawn down there is that the electrons are further away from the rod, and the positive charges, on average, are closer to that negative rod. Now, Coulombs law says what? It says that the force equals K Q1 Q2 over R squared. So notice my R values here, and I'll try and use 2 different colors. Notice that the average distance here to the protons, I'm going to call that R1, okay? And then the average distance to the electrons, I'm going to call R2. And what do we notice? We notice that R2 is greater than R1, right? So even though I have the same amount of positive negative charges still on the meter stick, the distance that those charges are to the excess negative charge on the rod is different now. And so how does that manifest itself? In Coulomb's law, if I look up here, right? Remember, let's write this here. As the distance, the average distance goes up, what happens? The force goes down. So if I draw a free body diagram of the meter stick, on the meter stick, then what am I going to see? Well, I'm going to see the following. Because these negative charges are further away, then they are going to exert a force. There's a repulsive force, right? So I could represent that with this red arrow, and I could call that F2, right? The repulsive force that you get from those negative charges being close to those other negative charges. But how does that force compare to the attractive force that the positive charges are going to feel from that negative charge? Well, the attractive force is going to be bigger. Why? Because they're closer. So if I draw this arrow, this is going to have a larger arrow, right? And this is F1. So since F1 is greater than F2, there's going to be a net force toward the rod. And that's what you saw in the demonstration, right? You saw me be able to move the glass rod. The glass rod basically attracted the meter stick to it, and it didn't matter which direction. When I switched direction and put it on the other direction, the meter stick would slow down and it would change direction. It was always being attracted to the rod. And now you see why. And you see why using the charge model and using also the idea of Coulombs law. Isn't that neat? Hopefully someone out there is smiling or has goosebumps or something. And let's talk about the paper dots really quickly, because I think that's another good one. I don't know that I have enough space here to do it. I'll just kind of carve something out here on the bottom here. So paper dots is really cool because with the paper dots also, you have, here's the rod. It's the same idea. The paper dot initially gets attracted to the rod, right, because of the same idea as the meter stick. But in this case, the paper dot actually comes into contact with the rod, right, because it jumps up. And so the cool thing is what happens, and I'll try and zoom in here, and I'm going to try and do my best here. I don't know how well I'll do. When this happens, then you actually get a jumping of negative charges from the rod over to the paper dot, okay? So in a matter of a split second, or maybe a second most, what you saw is you saw the paper dots would come up, and they would go back down, up and down. And what's happening is at first they're attracted because, like we talked about the meter stick, but as soon as some electrons get jumped on or jump over to the paper dot, then you have negative, excess negative and excess negative. You get a repulsive force. And so the paper dot kind of falls back down, or I should say gets repelled back down onto the table. And sometimes this can happen a couple times, or you can see it with a couple different paper dots, until basically the charge is neutralized, so to speak. You get the same amount of charge being deposited on the paper dots, on the tabletop as well, because there's transfer of charge there. There's also, by the way, transfer of charge into the air because the air has water molecules. And so over time, those effects kind of go away. But it's kind of cool for those couple of seconds, right, where you see the paper dots kind of dancing up and down, and then now you can see why. All right.